All right, here we go with unknown integrals. These are sad integrals. Nobody knows them. Just kidding. They can take up some paper and they can be a little bit tricky. So these are definitely ones that where you might want to work the same integral a couple of times to make sure that you can get where you're going and not have a big mistake or issue. So evaluate e to the x cosine x. Now, let's just keep a couple things in mind here before we get going on this. So number one, if you take the derivative of e to the x, so if I have y equals e to the x and I take the derivative, I get e to the x. And if I take the derivative of that, I get e to the x. On the other hand, if I integrate all of these, integrate, they integrate to e to the x. With cosine x, if I take the derivative of cosine x, I get negative sine x. And if I take the derivative of that, I get negative cosine x. And if I take the derivative of that, then I get, negative cosine, I get sine x. And if I take the derivative of that, I'm back where I started. So both of these guys lend themselves to repeating, and no quick, easy way to get out of it, okay? Well, going back to our tips and tricks, and keeping in mind how integration by parts works, where we're going to have the integral of u times dv. This is going to be uv minus the integral of v du. Okay? So while we're working on this part, remember that we wanted to pick u in very specific ways. Something where you took a derivative, it generally got easier, and something where you integrated, it generally didn't get much more difficult. So what to do here? Well, in our tips and tricks, one of the last things we wanted to pick to be u was a trig function. So in this case, we're going to let u equal e to the x. It was actually one of the ones that we wanted to try and use as a u. And so that means that dv is going to be cosine x. All right? So here we go. U equals e to the x, dv equals this. Integrate u, take derivative of u and integrate v. Hello, Sports Center. All right, so here's our initial setup. Okay, and what we're going to do is we're going to do our uv integral v du. So u times v, that's going to be e to the x sine x. Okay, minus the integral of v du. So that's going to be e to the x sine x. All right, so we can't integrate this guy either because we're basically the same place that we were right here. So we're going to do parts again. U is going to be e to the x, so du is e to the x dx. Dv is going to be the sine of x this time, and dx. So when you integrate sine of x, you get negative cosine x. So we're going to set that guy up the same way. So here we go. By the way, this is y equals. So now y is going to equal e to the x sine x minus, and looky right here what we've got. We need u times v. So that's going to be negative cosine minus the integral of v du. And looky here, we're minus e to the x cosine dx. All right. Well, now what do you do? E to the x cosine x, that's basically back to this guy, which is where we started. So what's going on here? Well, let's write it out and simplify it just a little bit. Y equals e to the x sine x minus negative e to the x cosine x plus the integral of e to the x cosine x dx. Can you see that we would keep going and keep going and keep going with this guy? We'll take one more step.
Do you want cherry?
Sure, I'll take cherry. Oh,
A cherry.
all right, that's okay. Good toss.
Not in sports for a reason.
That's all right. Okay, so to wrap up this question, I'm just going to make a small change here. I had to pause for a second, and I noticed these aren't y equals, by the way. Remember, when you're doing integration by parts, you've got this integral equaling this stuff. So for my integration by parts, my integral is equaling this stuff. So this is the integral of e to the x cosine x dx all the way down. So this is the integral of, all the way down right here, all the way down right here. So what we're going to do is clean up one more step on this guy. E to the x sine x plus e to the x cosine x minus the integral of e to the x cosine x dx. Now, remember what this equals. This equals the integral of e to the x cosine x dx. And notice one more time that this guy and this guy are exactly the same. So if we want to know what that integral equals, we can actually move this whole thing over by adding it to both sides. And when we do that, we get a brand new thing. We get 2 times the integral of e to the x cosine x dx equals, and then on the other side, we've got this e to the x sine x plus e to the x cosine x. And then if we divide all of that by the 2 right here, and add a c, we've got our integral. Because then when you look at the integral of this guy, e to the x cosine x dx, that is this answer inside the box. All right. So there's a few steps to take on this, and some of these can take up some paper and some space. But again, these are ones that if you practice just a little bit, you should be able to get to where you can get to the end and find where your integral starts to repeat itself so that you can simplify it. Okay, now that we've had a lot of exposure to integration by parts, let's just dive into this a little bit and prove that the natural log of x, the integral of natural log x dx is equal to x natural log x minus x plus c. And we don't have very much choice here. We pretty much have to let natural log of x be u, and we've got to allow dx be dv. So how does this shake out? Well, if u is equal to the natural log of x, then du is equal to 1 over x dx. And if dv equals dx, when I integrate that guy, I get v equals x. So when I do my integration by parts, and let's just have a real quick reminder, integration by parts is u times v minus the integral of v du, okay? So if I integrate u dv, this is what I end up with. All right, so here we go. X uv is going to be is x natural log x minus the integral of v du. So that's this part right here. So that's going to be 1 over x times x times dx. And then clean up this integral. So x natural log x minus the integral. And look, those x's cancel out. I'm left with dx again. Okay? So the integral of just dx, it's just 1. So that's going to be x natural log of x minus x, and then as always, since it's indefinite, plus c. And that's all there is to it, and that's using integration by parts, and this is one that we can handle. So some of our proofs now, we can actually prove some of the different integrals that we've just been given a rule for using parts. It's really a powerful way to perform integration. All right, here's one last integration by parts. This is a toughie because we're dealing with the differential equation dy dx equals the arc sine of x with an initial value of x equals 0 when y equals 0. So let's set up our integration by parts. The integral of u dv is equal to uv minus v du. Okay, so there's the setup right there. Well, if we deal with dy dx equals arc sine of x, I'm going to multiply both sides by that dx to start with. So I start here, and I multiply both sides by dx. The reason I do that is so I can get my integral action going here. So dy is equal to the arc sine of x dx. Okay. Now, when I integrate this, the left-hand side integrates really, really nicely. The left-hand side, and those are nasty-looking integral signs. When you integrate dy, you get y. When you integrate the other side, it's a little bit tricky. That's going to be our by parts, and I'm going to let u equal the arc sine of x. I'm going to let dv be equal to dx. And remember, when we're trying to determine what to set up to be u, at the very way up the list, very much so towards the top, are the arc sines, the arc trig functions. So when I take the derivative of the arc sine, I get 1 over the square root of 1 minus x squared dx. And when I integrate this side, v equals x. So when I do u times v, I'm going to get x arc sine x minus the integral of v du, and that's going to be x over 1 minus x squared dx. Now all I have to do is make a u substitution here, and just to help you out a little bit, if I have x over the square root of 1 minus x squared, this is the same thing as saying x times 1 minus x squared to the negative 1/2. So if I let u equal 1 minus x squared, du is going to be negative 2x, okay, and dx. And so what I need, I've got x dx. So I'm just going to move this 2 over and have negative 1/2 du equals x dx. Okay, back over here to this problem again. Let's set up my u substitution. So what's going to happen next is I'm going to have y equals x arc sine x minus, I'm going to use some parentheses here, and I'm dealing with the integral of u, all right, to the negative 1/2 times negative 1/2 du. Okay, this guy is not too bad to integrate. So moving on down, y equals arc sine of x, x arc sine of x minus, and then when I integrate this, u to the 1/2, so that's going to be plus 1, u to the 1/2 power now, divided by 1/2, okay, times negative 1/2. All right. And the 1/2s cancel out. If I divide by a negative 1/2 and multiply by a 1/2, they cancel out. And this negative make positive. So I'm going to substitute my purple u back in here, and I'm going to get my general solution. Y equals x arc sine x plus the square root of 1 minus x squared. All right, there's your general solution right here. And we can use this guy and create a slope field. And then now we're going to just check out this general solution. Well, what do? We simply take 0 and put it in for y, and 0 and put it in for x. Okay? And what happens is when you do this, 0 times anything is 0. So I end up with 0 equals 1 minus 0 squared. So 0 equals 1 plus c. C is going to be -1. So the solution for this guy, for this differential equation, is going to be y equals x times the arcsine of x plus the square root of 1 minus x squared plus c. Now, this is a rich problem. There's a lot going on here. And so maybe this is a kind of a problem where you need to try and solve it on your own. Come back to the video, come back to the notes, see where you need a nudge, start again, and see where, if you can get to the point where you can solve this problem without looking at anything for help. And it is difficult, but also it's totally doable. Just take it one piece at a time. Maybe you have some different colors to keep track of all the different stuff that's going on. Okay?